Okay, just waiting for the audience view update, and we'll say go. Okay, good morning, good afternoon, wherever you are in the world today. What I'm going to talk about today is really an introduction or overview of the various what we call Fledermaus data types, the objects that you see in Fledermaus, Imagic, and our associated tools, and a little bit about what they're capable of doing and when you use them and when you might want to use them, and so on and so forth. So let's begin. So really, as I said, it's going to be this is going to be an overview of the main data types that you see in Fledermaus. A little bit too of how they are similar or different to other software systems, like how a surface in Fledermaus may be related to a surface that you see in Esri or other GIS products. And we'll also cover on the sort of the second or the last third more of the pure file magic data type, which we use for quality control and editing and the cleaning process that it facilitates. So really, when I talk about what are Fledermaus data types, if you have a typical Fledermaus scene, it's this area in the lower left corner where you have your data sets. In Fledermaus, it'll always have a scene one, and then you'll have one or more different data types underneath it. And anytime you select these data types, there's always a series of panels shown to the right, which are the object attribute panels. And these panels, the number of them, what they contain, and the option presented change depending on what the object type is. I'll probably use the word object type instead of data type, because I'm specifically referring to the Fledermaus object types that we support. So what really are the object types? They're the building blocks of the scene, whether we look at it in Imagic, whether we look at it in Fledermaus. They're certainly the familiar types of visual imagery that you're used to seeing, pictorial rated raster imagery, surfaces from many different data types, your points, your vector types. And by vector types, I don't mean scalar plus direction. I mean vector and mathematical defined types like line, polygon, polylines, these kinds of things. Sometimes you'll see solid models, which we use for tracking vessels in a scene. They're just your CAD-like objects. And the PFM, which is the one we use for our data cleaning. And of course, there's actually many more than just these. These are probably the most some of the most common ones that you see every day if you're using this Fledermaus. So really, what does a data type support in Fledermaus? And it's a number of things. It's not just that it's an array of data from a surface or whatnot. A data type provides a storage model of how you store the data. For surfaces, it's a 2D array of values. For points, it's X, Y, Z attributes, so on and so forth. A data type or an object type is also responsible in Fledermaus for providing the visual methodology of that stored data. So how we present our surface data, how we present our points, how we present our polygons, and so on and so forth. Some of the data types are very static. They're just it's a data that's been, you collected a series of data and you want to just look at it. There's not much change in the data. There's not much interactivity with the object information itself. It's more of just a viewing metaphor. Some of the other types, the more complex types, are themselves highly interactive. You can do a lot of operations on the data itself. And the data type or the object types also support various operations on the data they contain. Surface objects provide a series of operations that are relevant to surfaces, points for points, and so on. In Fledermaus, we generally refer to these objects as the SD data objects, or scientific data types, just a historical reference. And we often talk too about scenes, which are a a collection of one or more of these SD objects. So there are actually a few data types that have no visual representation. They're more organizational in nature, and really there's three of these. And the most important one is we call the scene parent object in Fledermaus. It's the one that always sits at the top of the list, and it has the children objects underneath it. And what's critical about the scene is normally defining the coordinate system that you want to work in. And this can be separate from what the coordinate system of the various data objects themselves are. In this case here, I'm looking at a scene which is a WGS 84 UTM zone 30 north. That's going to be my working coordinate system. The vertical datum right now we just use for units. So you can have a coordinate system in the vertical can be meters, feet, fathoms, that kind of thing. That's what the vertical datum is actually used for. And another sort of important one is the two options for how do you display geographic coordinates and how do you display projected coordinates. If you're using geographic coordinates, this one's actually not. You can choose to show the more typical decimal degrees or more sort of navigation friendly degrees, minutes, decimal seconds, or degrees, decimal minutes, and so on. There's also an option that you probably have not seen or too many people use. It's actually the display mode that the system's operating in. Is it operating in a flat projection, or is it operating in a spherical, trying to wrap the data around the sphere to make it more Earth-like? Generally speaking, the spherical, there's only a small number of data sets that support rendering in the spherical mode, and the data has to be geographic normally for spherical to be useful. Usually that's data sets that encompass the bulk of the world, and some other options like the background and the foreground color and whatnot. There's a similar object which is like the scene. It's just a standard parent object, and it just facilitates a hierarchical list. So for example, if I want to turn on a set of data under ancillary data, I can create a parent object and drag and drop these objects underneath it, and I can show and hide the whole collection of objects at once. So certainly when you start to get a large number of objects, introducing the parent ones just help organize your data a bit. And again, that's just it. The summary of it. It contains a collection of other objects. The other thing that you can actually do if you have parent nodes is you can translate, move around the whole subset of objects in one operation. Where you in importing data, you sometimes see these used is when you're importing often CAD data or the S57 chart data, where a whole bunch of different line objects may be created. AutoCAD files often have many layers in them, and each layer becomes its own object underneath a parent. So it helps keep your an AutoCAD drawing a bit more together. And sorry for the quality of the graphics on this one here. The third type of parent object is when we actually work with on the Windows 32-bit version of the software. You can directly work with Esri Arc products, and this object manages the connection to the geodatabases, allows you to pull data in from Arc to create SD objects, and also the reverse, to push data from many of the Fledermaus types into Arc. So there's a set of common attribute panels that you typically see that are shared among every object. And I'm just going to do a quick review of those. And so most times when you load something in, the very first panel will indicate what the data type is. So this particular one I took a screen capture from, it's a plane. The bounds tab is a typical one. Every object has the data bounds, an X, Y, Z bounds. This is actually comes from a projection around in Antarctica, a special custom projection. That's why the numbers are a little unusual. And you can always see the bounds of data by typically the min and max ranges, but you can also change the georeference method to center and center and width, well, X width, Y width, and Z width, which is sometimes useful when you have things like a solid model representing a boat, and you want to control the size of the boat in the scene, set it to what you know is the right size. So every object has a bounds tab. Normally, you don't manually change these coordinates. They usually are part of the import process. The georeferencing tab, very important. And this is the important distinction here is different from the scene. In the scene object, you're setting how you want to look at your data. Well, I want to look at all my data as if it's geographic, or I want to look at my data as if it's in UTM zone 19. The specific georeferencing tab for any object indicates what that object is. So it says the data stored in this object, in this case, is a custom projection for that was used down in Antarctica. You do not normally, well, once you've identified your data as being in a particular projection, you do not change it by changing this. You change it by, setting how you want to look at it in the scene, and then using the reproject button to turn that data into whatever coordinate system you actually want to look at if it's not the same as the object one. Same with vertical datum. Just a sample of some of the right now the different units. Again, this is identifying what the units are of this object. Whereas if you said, say, the units of this object might be meters, but in your scene you've set it to say I want to see it in feet, then the system will automatically adjust the coordinates as displayed. Another panel that's pretty much shared among all objects is the time panel, and this is mostly for doing things like moving objects in space and in time, basically moving its position and orientation in time, changing its scale in time, changing transparency, turning objects on and off at different times, visibility, those kinds of operations, and you can, in conjunction with the time bar, build a whole dynamic visualization story. I'm not going to talk about how to do any significant movie making in this particular talk, but this is an important panel in that process. And really the last panel that's shared among pretty much every object is the info panel, and it's really per object metadata that's often created as part of the creation process. In this case, the author was Martin Jacobson, created on that particular date, and this was created in the other tools. We don't put too much information in this yet, but it's a growing. There'll be more going in the per object metadata as time progresses. Another one that's actually not in every object, but it is shared in a number, is the color map panel, and anything like surfaces, scalars, the PFM all make use of points and lines, all make use of color maps. And in this case, this is just showing the distribution of height data in a DTM, the color map, and it has tools to manipulate the color maps, edit color maps, and do quite a lot of control over how color is mapped to data. The shading panel is shared among a few object types, mostly the DTM or the surface object and the PFM. And it just allows you to set sun illumination directions and apply those lighting parameters to get a very nice visualization of your data. Okay, I'm just going to cover a couple of the most important objects, and then I'm just going to switch to Fledermaus directly to bring up some of these things. And then if people have some questions, that will be a good spot to address those. Certainly one of the most important object types that we use in Fledermaus, one of the original, well, the original one, is the surface object. And in general terms, it is a function z equals f of xy, where the xy points are sampled on in discrete steps. Most of the time we do uniform grids, but the software supports the x and y cell size don't have to be uniform. They can be rectangular. Many products will often refer to these with different names. If they're storing terrain data, it's often digital terrain model or digital elevation model. Sometimes I generalize them and just call them a scalar field, because you can have a surface of data other than heights. It could be temperature, a surface of pressure, and so on. The most important aspects of a surface is that they contain the two most important layers. They contain shape, that's typically the heights of the data or the depths, and they contain a color imagery layer, which is the illumination or the shading. That's what makes it look like a nice filled surface. Then of course you have your georeferencing, which positions your grid in the world and in whatever coordinate system you want. And there's also actually an optional, what we call a scalar layer, where you can attach to a surface, say the slope or the temperature, pressure, or whatnot. So you can, for example, have the shape of a surface but have it colored by the scalar value. Now, if people have been using the old version of Fledermaus 6, surfaces, the color data, the imagery data, and the underlying surface always had the same resolution. That is not true in version 7 anymore. You can have a much higher density imagery on top of a lower density surface, or vice versa, and that's very commonly used when you, for example, drape imagery on top of a surface. You drape aerial photo, or you drape an interpretation imagery on top of a surface. There is a restrictions currently with the attached scalar. It currently does have to have the same resolution as the underlying surface data. And I just make a note that the georegistration is cell center based, meaning that when you load a surface and you look at the bounds, you're seeing the X range from the lower left cell center to the upper right grid cell center. And the default display, and I'll demo this when I launch Fledermaus in a minute, is the cell center connected grid that gives you that smoothly varying surface. But there is a plates view option which shows the actual bins of a particular surface. That's kind of a repeat we had. The current version 7 surface replaces a number of object types that were present in the old the version 6. The original surface object, the texture map used to be separate data types. Now they're supported directly by one. So this is the actual attribute panel for a surface object. Again, you'll see a number of the tabs are the shared ones that are shared among all the objects. We'll actually change this name DTM to surface pretty soon, but these are the specific surface options. It's mostly control of the transparency and how you want to render it. Do you want to render it as a smooth cell center connected surface, a wireframe surface? Do you want to see the actual plates that make up that surface? A number of actions that can under this pull-down menu that operate on surfaces. A lot of export options to whether it's export to Google Earth, turning a surface into imagery for import or export to other products, whatnot, and a little bit of information about what the actual cell size of this particular surface is in its size. It'd be a pretty small surface overall. I'm going to just cover, there is actually a scalar object as well, which is separate from a surface in that it's similar in that it's a 2D array of discretely sampled values. It's generally not height data. It's often like say temperature, pressure, slope. Could be an interpretation model, whatnot, and and the trick is how is it visualized. It's because it's brought into a 3D system. You have say you have temperature, but you wanna bring it in the system where you have some other data that's surfaces that are based on height. Where do you put that scalar surface? And that's why it's visualized as a flat plane. The color of the surface is derived from the data stored, but you can set it as at a particular height in the scene, and I will show that. And I often like to think of these as becoming more common. It's becoming more common to store scalar data as a floating point TIFF image, which instead of storing imagery data, just color data, you're actually storing a specific numeric number, like slope, temperature, pressure. And the attribute panel is fairly simple in this case. You can choose where you want to put the scalar in the scene, at what height, and whether you want to show it as, again, a smoothly varying scalar surface, if you will, or the discrete samples of the cell. That's what the interpolated tag does. Okay, so I'm just going to take a quick break here, and just going to launch Fledermaus for a second. Aaron, is there any questions? I
haven't had any text questions yet. Well, Mark, guess that's set up. If anyone has any verbal questions, you can raise your hand or send in a text question if you like. I think you're good to go so far.
Okay, just be a second here. Surface object. So just a quick dynamic overview of that particular little surface sample here. In this case, my scene is a geographic scene. As I move my cursor, you'll see the coordinates are degrees, minutes, seconds, just down at the lower left corner. Same with all the bounds, how it actually shows the coordinates. You can choose, if I actually change this, for example, to decimal degrees, then when I move my cursor over the scene, that's the coordinates you'll see, and that's what you'll see in the bounds. Just a way to choose how you see the units. If I select the DTM object, mostly what I wanted to show in here is the difference between the modes. If I actually look at the plates mode, this is the actual underlying surface that's stored. You're seeing a series of discretely sampled bins with a particular height, given a color based on its height. Normally, when that shows you the complete coverage of the data set. When we visualize it as a shaded surface, we are essentially taking the center point of each cell that you see here and joining it with its neighbor, and that gives the smooth shaded value. So the complete coverage and the smooth shaded, which is typically how we view surfaces in a 3D scene. And again, tools that operate specifically on surfaces are normally available under the Tools menu, and often duplicated in the menu tools as well. And things like controlling transparency, obviously more more relevant if there's objects underneath it to see through, and just wireframe is just gives you an idea of the cell size. And that's a typical surface object. If I look at a scalar, just for comparison, I guess I don't have to quit each time, but I'm just used to it. A scalar, on the other hand, in this case, actually, this is surface data stored as a scalar. You'll see it's actually a perfectly flat object. It has no relief, and the actual information is stored in the imagery. It's very close to just being a plain imagery object. The only difference is it actually preserves the numeric values. So if it's slope, it would be the numbers you see at the bottom of the screen for the scalar would be degrees. If it was temperature, it would be the degrees Fahrenheit or the degrees Celsius, and so on and so forth. That floating point data is actually maintained in the scalar, and there's again, it's probably not high enough resolution, but you can treat it as again, like a surface, the discrete cells that make up the scalar, or if you choose the interpolated, it basically smooths it out to give the appearance of a continuous scalar. Often these scalars are attached to surfaces, and so you can drape it on a surface if you want. And then there's various export options to GeoTIFF. Now, a lot of these dialog boxes, there's extra buttons that appear if you have Arc on your machine with a valid license to Arc. A lot of these objects will have an extra button that has options to export this or push this scalar into an Arc database or a geodatabase. Same with surfaces, points, lines. Many of the objects have methods to directly push the data into an ArcView GIS, as opposed to having to say export the data as an ASCII file and then use import tools. It's just a much more direct approach. Okay, so back to continuing through the object types. GeoImage, it's really just an image. It's like a scalar, except it's our red, green, blue data. It's pictures. It's satellite imagery. It's aerial photos. It's digitized data. It's basically color or grayscale, and that's often brought into the system to be draped on surfaces or augment your understanding of a scene in any way. And it has very similar options to the scalar, basically transparency, and whether you choose to look at the pixels as flat pixels, or whether you want to blend the colors to make it look a little smoother. And typical information about the cell size of it's the pixel size and how big the imagery is. There's actually a number of imagery objects. If you can take an image in and put it so it's in the Z-plane and flat, you can also bring in an image and treat it as a vertical image, just oriented in the XY plane, basically given a start and an end coordinate and a height range, and it will bring that data into the system. There's also a vertical curtain, which is instead of just being a oriented plane, the vertical curtain actually has a geographic coordinate at each column of pixels, and so it can actually the imagery can follow a track, and that's often used visualizing seismic data that follows a ship track, or if you've done velocimeter profiles in the water, and you have a whole range of CTD casts that you've turned into an image, you can make that imagery follow the path. There's also, again, a slightly more sophisticated version of the vertical curtain, which is the beam curtain. And this is really used in conjunction with midwater processing tools. And when you have a sonar that you want to see, say, beam 5, it will actually make a visual curtain of the intensity returns. But it's, instead of being absolutely vertical, it's tilted in the direction of the beam. So it's really a tilted vertical curtain. The only reason why I say depreciated here is the vertical imagery and vertical curtain are now actually the same object. There's not. They used to be just two separate objects, but now they're just one. So there's an example of actually a vertical imagery of this is midwater data's returns just directly under basically the nadir beam feedback, and you can see how the imagery also has a lot of transparency in it, but where there's data, you can see how it curves around at the end. Basically, the imagery follows the ship track. That's a typical use of the vertical curtain object. The panel there's not too many options on the vertical curtain. Mostly, if it's just storing a flat imagery, you have a start and an end point. If it's a vertical curtain, then there'll also be a whole bunch of intermediate points, and that's prepared outside of Fledermaus. That's basically that one. Again, this is not a very good screen capture at the bottom of the panel. Another object related to midwater processing is the beam fan object. It's like an image, except it actually, what you're seeing is the actual ping data, and then there's options to, whoops, going the wrong way. Here, let me get back. There we go. There's actually options to choose, what beams do you want to view, what range do you want to view, depth gating, and then controls for the intensity mapping to eliminate the noise, so you actually see, in case that the fish traps in green up here. But this object, unlike some of the other ones, is actually dynamic in time. There's a whole series of these. Every ping is stored as a fan. So in Fledermaus, you can choose. This is just looking at one fan at a particular point in time, but it's actually fully dynamic, and the beam fan moves in time. Again, often used in conjunction with midwater, but doesn't have to be. There is actually a volumetric object in Fledermaus. It's just think of it like a surface, but a three-dimensional volume. It's a function of x, y, and z, and with the density values. In terms of acoustics, usually it's intensity return is a function of x, y, and z. And there's visualization choices for showing, selecting particular intensity levels, producing an isosurface, which is just a series of, it's like contours, but it's a 3D contour of volume data at a particular intensity level. And you can see in the bottom sample here, there's actually two isosurfaces at different intensities. This is the gas is being ejected from the underwater volcano, and there's other options to view the volume data as 3D slices. So you can look at an imagery, a particular slice in the X, Y, or Z plane. Although I didn't capture the panel. Those are the basic visualization options for the volume data. And there are tools in FM command to take, if you have any general data, X, Y, Z, truly volumetric, you can produce these volume objects. Another major object type that's used all the time, 3D points, and it's not, this is just a sample here of the actual series of beams and samples from this is, I guess, a 7125 system, and just chosen around around the rec. In this case, simply color-coded by depth, but the point format is actually the class itself. The object type is actually quite sophisticated. You can have, it's not just X, Y, Z, you can have any number of attributes associated with it. There can be a label associated with each point, and also an action, which is an action means when you click on a point, something occurs, which I can demo interactively a little later. You'll see again there's quite a few options for the points. There's here's how you look at each point: cube, a sphere, or just a dot, crosshairs, whatnot. There's how you choose the color. In this case, the color was chosen by just mapping it to height, but you could choose color from another attribute you have, fixed color, whatnot. Same with, you control the individual size of the marker for each point, so you can make the points vary based on, say, you had concentration of methane gas in a series of points. You could make the ones with more gas appear bigger. And same, the point object also supports data that varies in time, so you can identify a particular field, which is the time tag, and then you can actually if you use the time bar in Fledermaus, play the data, see how it evolves in time. And there's a few options that are typical with points. Sometimes we want to drape them on a surface. There's a lot of we bring in a lot of data from different GISs or AutoCAD data. Often it's just 2D point or line data, and sometimes we want to drape it on the surface. Options for that, exporting it, whatnot. Options to look at just a time window, so on. 3D lines, another basic type, and it's your simple lines, polylines, polygons, and it currently you can have an attribute associated with it. This is typically shape files that come from Esri or through a direct connection. A lot of their point, line, polygon data. This is how we bring it in. This is how we visualize it, and there are various options to support that, draping lines on the surface. When we do contours, for example, you're often producing a 3D line object. Again, another sort of building on top of the 3D line class, a much more sophisticated object type is the interpretation node, and it's something that can be, say you have a surface and you want to select the areas, select polygons, do in this case classification or interpretation. It interacts with the other tools that allow you to select areas, build up and build up either a polygon or a graphical map of the classification. It's rather than just having the data imported and visualized or worked with. In this case, you're actually creating data on the fly for a particular purpose. Another much more complex object type is the vessel object, which normally is used in conjunction with the vessel manager application to provide the real-time vessels moving through a scene. It connects usually to a navigation stream, passes the data to Fledermaus, and you can choose your model to represent, say, a ship or ROV or a diver with a navigation system strapped on his or her back. Whatnot. There are tools to measure distances from other objects in the scene or destinations. It can be tied in with the profile. Obviously, I'm not going to go into the detail about it in this particular talk, but certainly this is one of the more sophisticated objects. And then there's really, I'll go through really quick, a number of very simple ones which tend to support visualization or interpretation options in one way or another. Planes, putting a plane in the scene, setting it at a particular height. Often we use it when we have land and sea-based data to put a semi-transparent blue plane wherever the sea level is, and to make it clear that this part's water, this part's land. Mostly it's used in conjunction with the surface different operations, like I want to set a plane at this height and I want to see the volume or the area of material underneath that plane or above that plane, so on and so forth. Really, this is just a historic one. It's a simple 2D grid with a specific number of rows and columns that you can put in a scene, and there's other tools to move it up and down. This one's not really used anymore. It's more historic. There's actually a 3D grid, which is a bit more useful. You can actually drape a grid on a surface is typically what this is used for, and sometimes nice if you're actually trying to do, say, engineering on the seafloor, and you want to have, say, a 5 meter by 5 meter grid that's actually draped on the surface. That's a handy little tool that lets you do that. Mostly for making presentations, adding a label, and then you can use the other tools to move it around. This just lets you select it, select the font, that kind of thing. Again, shapes. This is really simple shapes. I want to add a box, cylinder, sphere, cone into the scene for some, maybe really highlighting a particular area. The camera attribute, which we won't worry about, it's something that normally appears when you start making movies. It adds, it records your flight path and is used then to render movies or help render movies. And so this is sort of a summary of the main object types and a couple of details. Now the object type. How is the georeferencing registration done? Is it the overall bounding box of the data? One's up top here where service I say cell center. It's because the bounds are the lower left cell center to the upper right cell center, whereas a typical imagery, it's actually the cell edge of the lower left cell edge to the upper right cell edge, just because that's how most products, especially the 2D ones, treat imagery. There's many objects that do support reprojection. So for example, let's say you have geographic data, but you want to look at it in UTM zone 19. You can load a surface in, you can load your geographic data in, and set your scene to be UTM zone 19, and then in the georeferencing tab of the object, basically say, reproject my surface now to the UTM zone of interest. We do not do automatic on-the-fly reprojection for surfaces because you're actually changing the data. If you have a uniform or specific cell size in geographic, that's not generally going to be uniform once you turn it into a projected data set, so it essentially has to be resampled on the resulting projection, which is why we don't do it automatically, because if someone flipped back and forth multiple times, you could actually lose precision if you weren't careful. There are a few object types that do reproject automatically and immediately on the fly. Mostly right now it's the points and lines. So if you have, say, a geographic point object loaded, and then you start changing the scene's coordinate system, the data will just automatically reappear in the new coordinate system as you select it. The ones where it says no here, you actually have to hit a button to make it change into the projection you want. And there are a few that, like planes, we normally don't reproject. We just I suppose we could, we just don't. right now. There are a few objects. While every object can do things like move in time, be turned off and on in time, there's a couple of object types that actually do the data evolves in time itself, and that's most notably is the surface series. If you have a series of surfaces that change over time, you've created a surface series object. That's obviously one of them. Points, lines, the beam fan, the beam curtain, and the vessel object are all ones where the actual stored data of the object can optionally vary in time. And the spherical scene, again, if you have geographic data, there's a few object types, mostly the surface and the points and lines, the vector data that will automatically can be represented on an Earth-like sphere. That's the basic stuff before PFMs. And do a little bit on PFM. Is there any questions about basic object types, Aaron?
We did have a few questions over text. You're getting kind of short on time, so if you want to go on to the PFM
it's going to be about 10 minutes to do the PFM. So.
Okay. There is one question, and I answered it, and I'll answer it, and you can add to it if you have any additional to add. And it was just about surfaces, scalars versus DTMs, and the question was, how do you get scalar data in? The answer is you import scalar data. If you have it as, say, an ASCII XYA file, you would import scalar as a grid, and then in the last screen it asks you if you want to create a scalar SD or a surface SD. When you create a scalar SD, then you'll create the kind of flat grid that Mark showed in the demonstration. Do you have anything else to add on that?
Nope, that's correct. That's the way they're normally produced. Often the other way they get in is people have floating point geotiff data, and they want to import that data. It can be imported as a scalar, I believe.
And the other option is to create scalars internally. We have two scalar creation algorithms. The first is a slope algorithm, and the second is rugosity. And the output from that is you typically choose to output them as a scalar.
Yep.
All right, I think that's good for now, Mark. You can continue.
I think I'll just go right to the PFM, and then I'll stop at the end if people want to see some stuff in specifically in Fledermaus. So really is all I'm going to cover with respect to PFM. This is not a course on how to use it to do cleaning. It's really just to highlight the structure and how it's a little bit different than the typical SD objects. And the biggest difference is it's unlike everything that I talked about before, all the data is stored. When you say save an object, it's stored inside the SD object itself. That's not true with this PFM data structure. You're essentially making this often very large on-disk data structure to facilitate these large volume QC operations. So unlike a PF or an SD object where you could just stick it on a USB stick and move it to another machine, a PFM is actually a directory structure, and while you can move it, you actually have to use after you move it, you have to use tools to update all the internal pointers. It doesn't move nearly as easily as an SD file does, although we certainly support tools to move them. And this is really kind of a quick top-level diagram of what a PFM, and it can be, you have a whole series of source data. It usually comes from survey data, multi-beam data, LiDAR data. Could be lots of XYD data. Typically, though, at its lowest level, it's X, Y, Z data with sometimes with backscatter intensities or not. Sometimes with other parameters and flags to say whether the data is good, bad, or potentially bad. And the process of building a PFM, which is normally done inside the Magic tool, it produces this data structure, which I'm just going to call mysurvey.pfm, and which is really a directory. And inside it, it has a number of different files. Two you always see, a bin file, an index file, a hypotheses file. Generally, you see those three, and optionally the target and audit file. Together, these make up what we call the PFM structure. The bin file is used to visualize, your surfaces, your density fields, your slope, whatnot, of your data, and it's also used to spatially access the individual points. So as the system builds the PFM, it reads out from, in this case, the sample here, all the multi-beam data. It actually loads it into the index file, but it's not just dumped into the index file. It's actually spatially organized in this index file. So if I select an area from my visual representation of the bin, it knows how to go and pull out that data and display it and allow you to make choices about whether the data is good or should be rejected for whatever reason. I don't have the line back. Once you do these operations, in many of the source formats, you can propagate those changes back to the multi-beam data. So you do all your cleaning, your QC analysis, working on the PFM data structure, and you can push those results back to the original files, because most of the original, or many of the original formats actually have rejection flags as part of it. That way you don't have to convert your data to yet another output format after it's been cleaned. Now, not all formats support pushing data back. If you just had ASCII XYZ data, there's no flags, so that's sort of a one-way trip. You can make the PFM, you can do your editing decisions, but you have to, when you write it back, you just create a new ASCII file with the clean data in it. And there's a lot of products too that can be directly produced from the PFM data set itself. If you're familiar with Cube and those cleaning processes, that's what uses the hypotheses file here. It's very similar to the bin file and stores the best estimated surfaces, and in areas where there's the data disagrees, there's a lot of some data at one height and another collection of data at another height. It creates its multiple possible surfaces from that. Again, it's really part of the cube process. And there can be associated target files if people have picked out, maybe they've also gone over the area with a side scan, or they have a charted file of potential targets that can be loaded and used in a target file, and some of the filters pay attention to targets and how they work with the individual data. And there's also an optional audit file which basically tracks changes of the edit changes at various levels if you choose to turn it on. Okay. So on disk, really, this is just what it looks like. You've got when you actually make a PFM file, this is just, I guess, a capture from a Mac screen. It creates a .pfm file, but it also creates this directory .pfm.data, and it's inside that where it creates its bin, index, control, line files. Generally speaking, you should have no reason to look at this data. You're welcome to, but if you change its name or do things like that, you will definitely mess things up. The control file really and line file really contain, well, it's really the line file contains the list of all the files that have been added, the data types, whether it's like GSF or HDCS or FAU or whatever source input formats. Normally, the only one at the user level you access is the .pfm file. And you should note that when you load a PFM into Fledermaus, import PFM, you can actually save an SD file. So now you have your, say, GELUTM.SD, but what's important to realize is that SD file is really just a pointer to the larger PFM file. So if you send the PFM file, that little PFM file, to somebody else, they won't be able to access the PFM. You'd have to include the whole kit and caboodle. Yeah. So that's just how it sits on disk. And visually, it's when you first load it, if you remember, if you're a user of version 6 with PFMs, it used to have a very small little coverage map inside the PFM panel. Now, whenever you load a PFM, it doesn't, remember this is designed to be a disk-based structure that's quite huge, potentially much more than you can load into memory. So we just, starting out, show the overall coverage map. The pink areas are where there's data available. You can use the tools to select an area, bring up the, well, do it like this. In this case, that's all the data selected, brought in. This is just a very quick sample I did, so it's not very high resolution. Again, we're looking at the data. There's options to, how you want to visualize it, very similar to the surface object. The shading panel I talked about, the color map panel I talked about before. Sorry, going back to the panel here. You can see there's a whole bunch of options for what surface do I want to look at, shallow, average, deep surface, how you want to color it by. There's a whole bunch of attributes that the PFM stores, the sounding density, the standard deviation, lines, flags that have been edited, whatnot. And when you run different filters, you can show points of the, where in the PFM those things have been edited. If you're working with targets, they don't have a target file here. You can create a targets file, set a targets file, and it'll load in all your set of targets. There can be snippets associated with it, and little images associated with the target. If it was, say, a side scan screen grab or something like that. And then the filters tab is again another part. PFM, unlike some of the other objects, is quite a sophisticated object in its own right, and has lots of different options for in this panel, running different filters on the data for cleaning. When I think later on Duncan is going to do a full tutorial on doing PFM and cube-based processing, and we'll actually go into the details of that data type. And that's the overview of most of the object types in Fledermaus right now. I'm just going to bring up Fledermaus, and if anyone has any specific questions, I'll just pass it on to Erin for a sec.
Hi, Mark. Yeah, there were a few questions that were on text. A lot of them involve some follow-up, so I might take those offline. But one of the questions was about the interp object, whether that was something that was imported. And all the objects that Mark talked about today are all Fledermaus object types that we create. So some of them are created from imported objects, such as a GeoImage. You import a TIFF and it becomes a GeoImage SD, whereas the interp object is something that is created directly in Fledermaus. So Mark can show you where that button is.
Yeah. I'm actually just going to do a couple things with my simple surface. I know the surface is geographic, but I want to work with it in UTM, and I do happen to know that it's already in it's in zone 19. This is a small little area in Portsmouth. Quickly, and this is I wanted to do this as well because this is what typically happens with a surface. I've just changed my scene to be UTM zone 19, and basically, where's my scene gone? And if you actually look, you'll see down here it says the object undisplayable, and it's in red. And the reason why it's undisplayable, if I actually click on it and look at the georeferencing, it's because the object's is geographic data, but my scene is in UTM zone 19. And as I noted, surfaces don't reproject on the fly or automatically. You actually have to push the button, reproject the scene. Well, if I do that, it will actually transform the data now from geographic to be UTM Zone 19 data. Now it's actually modified the data. If I save this object now, I'll be saving it as UTM Zone 19. The trick you never want to do is often people accidentally come here and just select this and change this to, from instead of hitting the reproject to scene button, they actually try and change the horizontal coordinate system here, which is never what you want to do. This is only about identifying what the data is, and in the next version of Fledermaus, we're going to make this a little bit harder to change so people don't do that accidentally. I'll see if I can do. The question was about interpretation. Interpretation is normally something you create. And you'll see the two menus sort of importing data types, different, like import data as points, lines, whatnot. But some of them are create, like create a plane, create in this case, add an interpretation. So I add an interpretation node. By default, it's basically an empty object. So I have my surface and I have my interpretation, and I'll just gonna very quickly. I'm not gonna bother changing. Let's sand, gravel, whatever. Yellow or something different. And I said it's sort of used in conjunction with other tools. If I take one of the selection objects and let's say drag around this guy here and select gravel. So I want to say this is going to be is gravel. Add. And you'll see it put basically a blue line around that area. I could go over and select sand, select an area out here and say add this as sand. Again, if you sort of do sloppy selections, add again as sand. You'll see it detects the intersection between the two panels. So basically, I'm building up a data type. I go over and say I want more gravel, and this area over here, for whatever reason, I think is gravel. Add it, and you can select select areas and do the opposite command too. Remove it. I'm just not going to spend too much time on actually making an interpretation. And then there's various. There's a bunch of options for in this case, preserving the polygons, exporting it, creating a graphical image. If you want to actually then create say a geotiff of not just the polygons, but say filled in with the various classifications, you can do that kind of stuff. In this case, I'm actually building up the data inside the interpretation object. If you had an ARC license as well, there would be options to push and pull these data sets directly from ARC without any really import style operations. That answer that question? That's not. It's not really a tutorial of.
Yeah, no, that was fine. We have, if somebody is interested in the interpretation feature, we have a full webinar tutorial about how to use that. And there's also a really good description in the reference manual that is installed with the software that tells you where it is and how to use it, how it works. So if you do have a question about that object in particular, just you can email me and I will get you more information.
The last two ones I'll show real quick, just because this is a sample of a point object that actually has a lot of different attributes associated with it. This is an export from the FM geocoder. You have a point object that has gradient, intercept, means, impedance, roughness, whatnot. So you can choose to, for example, I've just chosen it as a sphere to look at, but my color is my color is roughness, my color is whatever. Cycle through them. You can actually turn on the color map and then the ranges become sort of a bit more meaningful. The points can just be a fixed size. They slide by the size radius, but you can actually map size to one of the attributes. So, for example, if you map size to roughness, the relative size is now controlled by the difference in the object types. So you can see sort of which ones are clearly more rough than other ones. Just an example of a point with quite a series of options. And when I mentioned that points can also have actions associated with them. Unfortunately, these are all in different coordinate systems. Otherwise, I'd load them to sort of different areas of the world. Here's a really quick example of points. Not a very exciting set of points, but it's actually got an action map to it. In which case, if you're in select mode, and I actually click on any of these objects, the action is just to run the Windows Explorer window here. You see, I click and the Explorer window popped up. That's not very useful action, but people often use these, for example, to load data into the scene. So they may have a long river channel with a whole bunch of imagery along the river, and they can put points along it and click on the points and load the imagery into the scene. Or if you have a scene with sensors in it and you have tools you want to run when you click on an object, you can sort of use Fledermaus as a nice graphical front end to launching these tools. It's sort of an object not too many people are aware of. So I thought about it. Anything? Guess that's really all, unless anyone has specific questions anymore.
We had, again, a lot of stuff that is going to involve some follow-up, and none of it was really basic that I can kind of bring out for everybody. If anyone wants to raise their hand and ask any final questions, you're welcome to. The other thing I wanted to mention is that our next webinar is in November. We don't have it up on the website yet, but it will be concerning the hydrographic workflow. So working with those PFM objects that Mark discussed, using Cube and doing QA and QC for hydrographic workflow. It will be November 17th, and I think it's 3 p.m. GMT. You'll all be getting emails, and it will be up on our website, but I wanted to give you guys a heads up. I don't see any hands raised, so finally, if you did submit a question and I told you I would get back to you, I will. I'll send you an email at some point later today. And if you come up with any other questions, you can email me, eheffron@ivs3d.com. If you have a bug, please email support, because I am not support, so I just send it to support, and you'll get faster and better response if you send it directly to support. So that's support@ivs3d.com. I think that's all for today. Thank you, Mark, for the presentation.
Thank you for everybody's time.
Yeah, thank you all for coming, and we hope to see you again. All right, that concludes it. Thank you.